तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will look at solving linear programming problems. We will start by considering a simple example and then see first the graphical method to solve linear programming problems. The problem that we will take up is to maximize (6x1 plus 5x2) subject to x1 plus x2 less than or equal to 5, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. You may recall that this is the problem that we formulated in our first example. We will first see the graphical method to solve this. So, I am sure you would have learned how to draw graphs corresponding to inequalities earlier. We will do that. Now, let us first try to represent both these constraints in the form of a graph. We call this x1 and x2. We are only looking at the first quadrant because we have both x1 and x2 greater than or equal to 0. So, we will not look at the remaining 3 quadrants. So, we first try to represent x1 plus x2 less than or equal to 5 in the form of a graph. So, we first draw x1 plus x2 equal to 5. So, we try to identify 2 points that are on the line x1 plus x2 equal to 5. So, the 2 easy points would be 5 comma 0 and 0 comma 5. So, we draw the line, this is x1 plus x2 equal to 5. Now, this line divides the quadrant into 2 regions, one which will be less than or equal to 5 and the other greater than or equal to 5. The origin 0 comma 0 being less than 5 would mean that this is the area which is x1 plus x2 less than or equal to 5. So, we just mark the region x1 plus x2 less than or equal to 5. Now, we try to plot the other one 3x1 plus 2x2 less than or equal to 12. So, we first plot 3x1 plus 2x2 equal to 12. So, 2 corner points that we can think of are 4 comma 0 here, this is 5 comma 0, this is 0 comma 5. The other one is 0 comma 6 which lies on the line 3x1 plus 2x2 equal to 12. So, we draw the line joining this. So, this is the line 3x1 plus 2x2 equal to 12, this is x1 plus x2 equal to 5. Again this line divides the first quadrant into 2 regions, one which is less than or equal to and the other greater than or equal to. So, once again we look at evaluate 3x1 plus 2x2 at 0 comma 0 and realize that this is the portion that is to the left of it is less than or equal to 12. So, this is the region which is 3x1 plus 2x2 less than or equal to 12. You can see this on the graph sheet as well here. You find that the first one is between 5 0 and 0 5, the other one is between 4 0 and 0 6 which is shown here. The shaded region shown in this figure is actually the region that is common to both these constraints, this constraint as well as the other, and that alone is shown here in the shaded form. So, in this graph you will see that this represents the region which is common to these two. So, this two constraints are now represented by this region which is shown in this graph, and this is the point of intersection which is 2, 3. Now, let us look at this region. Now, every point inside this region satisfies both these constraints. Now, for example, if we take a point say 1, 1 which is inside this region. Now, 1, 1 satisfies both these. Now, 1, 1 has an objective function value of 6 plus 5 11. Now, we are interested in trying to maximize the value of the objective function. So, what we can easily do is, if we are considering a point 1, 1 here, you could always move either in the right or in the upward direction or left or downward direction and start moving and trying to see if there are better points than the point that we have chosen. So, if we take 1, 1, because both these coefficients are positive, it is possible either to move in the right hand side direction or in the upward direction to get points which are better than 1, 1 with respect to the objective function 6x1 plus 5x2. Every point inside this region satisfies all this. We also know that every point outside this region violates at least one constraint. For example, a point here would satisfy x1 plus x2 less than or equal to 5, but would violate 3x1 plus 2x2 less than or equal to 12. So, our region of concern and interest is only this shaded region. So, if we now try to get better points by moving either to the right or to the or above, then we realize that the farthest we can go is actually up to the boundary of this region. Or to put it simply, for any linear programming problem, for every point that is inside this region, there is always a point on the boundary which will dominate that point with respect to the objective function. If there is a negative coefficient, then you would move either to the left or below depending on whether it is for x1 or x2. If there is a positive coefficient, then it is always advantageous to move to the right or move to the top to find a point which is on the boundary. Therefore, we can now say that even though every point in this region satisfies these two constraints, because we have an objective function which is linear, you will have a situation where we are interested only in the boundary points, because for every point inside this region there is always a point on the boundary which will be better with respect to the objective function, even though all these satisfy the constraints. So, our focus immediately shifts now to only looking at all the points which are on this boundary rather than points which are inside this feasible region. Now let us look at a point on the boundary. For example, we consider this point. Now, with respect to this point, because if we draw this objective function line, slope of the objective function line being different from the slope of this line, we can always show that a point which is above or below will now be superior with respect to this objective function. Therefore, what will happen? For example, if we try to draw the objective function line 6x1 plus 5x2 so equal to some number like 30, a convenient number, then we end up getting 2 points 5, 0 and 0, 6. This is 5, 0, this is 0, 6. So, this is the objective function line. If we draw the objective function for a value like say 25, then you will find another line which is parallel to this, which will have value 25. Now, it is always possible to show, because these slopes are different, for every point on the boundary there will always be points which are above or below lying on the line, which will be better with respect to the objective function. So, this brings us to the point that we are now not interested in any point that is on the boundary, but we are only interested in the corner points. Now, in this example we have 4 corner points. Therefore, the corner points are the points that will dominate every point, or alternately for every point that is inside this region, it is always possible to identify one corner point which will be better with respect to the objective function. So, the 4 corner points that are of concern to us are 0 0, 4 0, 2 3 and 0 5. Now, the moment we identify the corner points of this region, all we need to do is to find out the value of the objective function for these 4 corner points. Now, for the point 0 comma 0, the value of the objective function is 0. For the point 4 comma 0, the objective function value is 4 into 6 plus 5 into 0, which is 24. For the corner point 0 comma 5, the objective function value is 25, and for the corner point 2 comma 3, the objective function value is 2 into 6 12 plus 3 into 5 15, which is 27. So, among the 4 corner points that we have, this corner point has the maximum value with respect to the objective function, and since we are trying to maximize, we realize that this gives the best solution for this example. We can also get to the solution in an indirect way. For example, if we draw the objective function line for, say, we have already drawn it for 30 and 25, suppose we draw it for, say, 15, then we will have the objective function line once again parallel, and it will be something like this. Now, we are interested in maximizing our objective function. So, we want our 6x1 plus 5x2 to try and take as big a value as it can. So, if we try to increase the value of the objective function from, say, 15 and above, you will see that this line is actually moving parallel to itself, but in this direction. Now, as this line moves in this direction, this line at some point will leave this region and go away, and it will leave, when it actually leaves this region, it will touch a corner point and then it will go away. Now, that corner point which it touches last before it leaves the region is the best value, and once again you can show that the same point 2 comma 3 is the point. As this line moves parallel to itself, the last point of the region it will touch is 2 comma 3, and this 2 comma 3 is the best solution for this problem. So, this is how the graphical method works. But let us also try to introduce some terminology using the graphical method. So, if we go back here, you will see the same thing that is happening. Here you will see that the objective function is plotted for values, say, 12 and 20. You can see the 12 line is here, the 20 line is parallel, it is here, and as it moves you will see this is the feasible point that has the highest value of the objective function and is optimal. We will try to define these terms called feasible, optimal, and so on. Yeah, next slide. So, in fact, before we do that, let us also define some terminology, as I had been saying. The first important thing is this region, the common region which satisfies all these constraints, is called a feasible region. It is called a feasible region. Every point inside the feasible region is called a feasible solution. And the best solution that we have identified at the end is called the optimal solution. Or optimum. In fact, both mean the same and both are used interchangeably. So, what we need to do is first identify the feasible region by plotting the constraints, and then try to find out the corner point solutions which are feasible solutions. They are also called basic feasible solutions, we will see that later. Right now we identify the corner point feasible solutions, and then the best among the corner points with respect to the objective function is the optimum. So, this is the summary of the graphical method. Now, to go back to the summary, next slide. Yeah, the graphical method works as follows: plot the constraints on a graph, plot also the non-negativity constraints, that is, restrict yourself to the quadrant where both x1 and x2 are greater than or equal to 0, which is the first quadrant. So, you do not have to plot anything in the second, third and fourth quadrants. Now, identify the feasible region that contains a set of points satisfying all the constraints, identify the corner points, evaluate the objective function at all the corner points, and that corner point which has the best value of the objective function, maximum or minimum depending on the objective, is optimal. We can use the term optimal or optimum respectively. So, a graphical method works very well. It is a very easy method to solve linear programming problems. It has one very serious limitation. The limitation is that you cannot solve for more than 2 variables using the graphical method. So, if you have a linear programming problem with only 2 variables, irrespective of the number of constraints, you can still solve it using the graphical method. So, the next slide would tell us we now need to look at a method which is better than the graphical method, which can handle more than 2 variables. The graphical method cannot be used if we have more than 2, if we have 3 or more variables. So, we need a method which can handle multiple variables. Now, what we are going to do is we are going to show the algebraic method, which is the next method, but we are going to illustrate it using the same example, so that we can understand how the algebraic method works with respect to the same problem, and what are the relationships, or what is similar and what is dissimilar, or how we see all these solutions coming in the algebraic method. So, we will also show the linkage between the graphical and the algebraic method by considering the same example. Now, let us go back to the algebraic method. Now, we look at the same linear programming problem. Right now, what we have to do is we need to solve these inequalities, because the solution to this problem is actually a value of x1 and x2 which satisfies both these, which means we need to solve these 2 inequalities. Right now, we assume that we do not know how to solve inequalities. We also assume we know how to solve equations. So, what we try to do is to convert this inequality into an equation. So, this is first written as x1 plus x2 plus another x3 equal to 5. Now, this x1 plus x2 should be less than or equal to 5. So, to make it equal to 5, we can add an x3, and because x1 plus x2 is less than or equal to 5, this x3 is also greater than or equal to 0. Because if x3 is negative, then it would mean x1 plus x2 is more than 5, which we do not want. So, the inequality x1 plus x2 less than or equal to 5 is now rewritten as an equation x1 plus x2 plus x3 equal to 5, and the condition that x3 greater than or equal to 0. Similarly, the inequality 3x1 plus 2x2 less than or equal to 12 is now written as 3x1 plus 2x2 plus x4 equal to 12 and x4 greater than or equal to 0. Therefore, the problem now becomes maximize (6x1) plus 5x2 subject to these equations under the condition x1, x2, x3, x4 greater than or equal to 0. In fact, this representation is useful to us because the new variables that we have introduced are also greater than or equal to 0 and are consistent with this requirement. Now, how do we define these variables in the first place, and secondly, do they have any effect on the objective function? Now, these variables that are used or introduced to convert the inequality into an equation are called slack variables. They are called slack variables. Now, we have 2 slack variables x3 and x4, which have been used to convert these inequalities into equations. Now, do these slack variables contribute to the objective function? Now, what do they represent? Do they have any physical meaning like the decision variable? Now, in this problem, x1 and x2 would represent the number of tables and chairs that the carpenter or the producer makes. Now, what does x3 indicate? What does x4 indicate? For example, if the person makes say 4 tables and 0 chairs, if the person decides to make 4 tables and no chairs, then this resource, where 5 of this resource is available, 4 of this resource is going to be utilized. Now, x3 takes value 1, because x1 equal to 4, x4 equal to 0, x3 takes value 1, and this 1 is nothing but any resource that is not fully utilized and left available at the end of the problem is represented by the slack. Now, we are going to make an assumption that such a resource is not going to add to the profit of the carpenter or the producer. So, the slack variable contributes a 0 to the objective function. Even though it is available as unspent resource, this is not going to add to the money that the person is going to make. So, slack variables as a general rule do not contribute to the objective function. So, you have a 0x3 plus a 0x4. So, now this problem is complete. We have two equations, we have 4 variables, we have the additional condition that all 4 of them should be greater than or equal to 0, and we have an objective function which has been written in terms of all these 4 variables. Now, we should solve this problem, and we also realize that solving this problem is the same as solving this problem. The only thing is, here we assume that we do not know how to solve inequalities. We have now converted it to equations. We at least know, we assume we know to solve this part. We will see how we solve the whole thing. Now, let us look at this problem. Now, this problem has 4 variables and 2 equations. We will assume now that we know how to solve. For example, we have 2 equations, so we can solve 2 variables using 2 equations. Right now, we assume we do not know to solve 4 variables and 2 equations. So, what we have to do now is, if we want to solve this, we want to solve 2 equations at a time. Now, to do that, we need to solve for 2 variables at a time using the 2 equations. So, we need to fix 2 out of these 4 available variables to a certain value, so that we rewrite it in terms of the 2 variables that we want to solve. For example, if we want to solve for x1 and x2, we can fix x3 and x4 to some arbitrary value and then rewrite it as 2 equations involving only x1 and x2, which we know how to solve. Now, to do that, there are 4 variables, 2 equations, which means we can solve only for 2 at a time. So, we can do this in foresee 2 ways. For example, the first out of these foresee 2 is solve for x3 and x4 by fixing x1 and x2 to some arbitrary value. The second one would be solve for x2 and x4 by fixing x1 and x3 to arbitrary. For example, I am going to write another thing called fix. So, here I would say fix x1 and x2 to some value, so that you can solve for x3 and x4. Here you fix x1 and x3 to some values, solve for x2 and x4. Similarly, fix x1 and x4 to solve for x2 and x3. The fourth problem would be fix x2 and x4 to solve for x1 and x3. The fifth one would be to fix x2, x3 to solve for x1, x4, and the last one would be to fix x3, x4 to solve for x1, x2. Now, these are the 6 problems that I have mentioned here by saying that you can solve it in foresee 2 ways. Now, the next question, if we take the first one, if we decide to fix x1 and x2 to some arbitrary value and then solve for x3 and x4, even this can be done in many ways, because these x1 and x2 can be fixed to any arbitrary value. So, the easiest thing that we can do is to fix them to 0. In fact, when we fix x1 and x2, the only thing we need to make sure is we do not give them negative values, because we do not want to violate this. We want our final solution to be feasible. So, we do not want to give negative values here. So, the only condition is when we fix x1 and x2 to some arbitrary value, you can give any non-negative value. Therefore, this problem alone can be solved in infinite ways by fixing x3 and x4 to any arbitrary non-negative value. The easiest thing that we can do is to try and fix them to 0. If we now force the condition that whenever we are fixing something, we fix them to only 0, then we get exactly 6 problems and 6 solutions, one corresponding to each problem. So, let us see what happens to this when we fix all of them in each problem to 0 and see what happens to the solution. Now, the first thing that happens is this. If we fix x1 plus x2 to 0, which is the first problem, we straight away get x3 equal to 5, x4 equal to 12. So, the first problem is x1 equal to x2 equal to 0, we get a solution x3 equal to 5, x4 equal to 12 and z, the value of the objective function, is 0. Now, let us look at the second problem. Second problem, we fix x1 and x3 to 0. So, x1 equal to x3 equal to 0. So, x1 x3 equal to 0 gives x2 equal to 5. Now, go back and substitute 2x2 is 10, this is 0. So, this is minus 2, x4 equal to 2 to give you z equal to 25. The third one, we fix x1 equal to x4 equal to 0. So, x1 equal to 0, x4 equal to 0 would give x2 equal to 6. Now, substituting here x2 equal to 6, x1 equal to 0 gives x3 equal to minus 1. I do not evaluate the value of z here because I do not have a feasible solution here. It does not make sense for me to spend the extra effort to evaluate the objective function for this solution, because I am interested only in feasible solutions. This is not feasible. The value that a variable x3 takes minus 1 violates this condition. So, this solution is not feasible. So, I look at the fourth one. Fourth one has x2 equal to x4 equal to 0. Now, x2 equal to 0, x4 equal to 0 here gives me x1 equal to 4. Now, x1 equal to 4, x2 equal to 0 gives me x3 equal to 1 and z equal to 24. The fifth problem that I solve now has x2 equal to 0, x3 equal to 0. So, x2 equal to 0, x3 equal to 0 gives me x1 equal to 5. Now, x1 equal to 5 makes this 15. So, this would make x4 minus 3. So, once again I get into a situation where I violate this condition, therefore, I do not have a feasible, this problem is not feasible or this solution is not feasible, therefore, I do not evaluate the value of the objective function. The last one is x3 equal to 0, x4 equal to 0, and for this example now, which means I have to solve x1 plus x2 equal to 5, 3x1 plus 2x2 equal to 12, which is slightly more involved than any of the 5 cases, and you finally get the solution here, which gives me x1 equal to 2, x2 equal to 3. So, 6 into 2 12 plus 15 z equal to 27. So, what we have now done is we first converted the inequalities to equations, and then we realized that we have now more variables than equations. So, we said we can, since we have only 2 equations, we can solve only for 2 variables, which means we have to fix the remaining 2 to some arbitrary value, and then we realized that each of these can be done in many ways, and then we reduced our search to the only condition that if we fix some values to some variables to a known value, then that value is 0, which means we end up getting only 6 problems. Now, we have solved all the 6 problems and we have got this. Now, these 6 solutions, we find something very interesting between these 6 solutions and the solutions that we obtained using the graphical method. Now, if we quickly go back to the graphical method and try to draw the graph again, we had something like this. We had one graph like this, we had the other coming something like this. So, let us assume this is the 2 comma 3, this is the this is 0 comma 5, this is the 4 comma 0, this is the 0 comma 0. If we go back, we can see the relations. The first one is x1 equal to 0, x2 equal to 0 is shown here. The second one is x1 equal to 0, x2 equal to 5. This I call it as 1, this I call it as 2. Right now we do not consider this. This we call as 3, which is x1 equal to 4, x2 equal to 0. This is 3. This is your, I am sorry, this is your point number 4, and this is 6. 3 and 5 are not represented here because 3 and 5 do not give us feasible solutions. So, there is definitely a one-to-one relationship between the algebraic method that we have right now seen under the condition that we fix them at 0 and the graphical method. Now, the 4 corner points that were of importance to us are now seen right here when we fix these to 0. So, on one hand it kind of validates our assumption that it makes sense to fix at 0, but on the other we need to explain why fixing to 0 has the same one-to-one relationship between the graphical method. Now, the relationship is also reasonably obvious. 1, any point that is inside the region we said will be dominated by a corner point. So, any point inside the region implies that this does not consider your x3 and x4. So, any point inside this feasible region implies that you are actually fixing x3 and x4 to an arbitrary non-negative value, and then you are solving for it. So, you are actually inside. For any arbitrary non-negative value that we fix here, we actually end up evaluating a point which is inside the feasible region in the corresponding graphical method. So, every corner point is evaluated by fixing these things at 0, so that we are able to solve the corresponding equations. After all, every corner point is got by solving the corresponding equations. This corner point is got by these two equations, x1 plus x2 equal to 5 and 3x1 plus 2x2 equal to 12, which means you are fixing x3 and x4 to 0. For example, this corner point is obtained by fixing 3x1 plus 2x2 equal to 12 and the x1 axis, which is fixed x2 equal to 0. Therefore, we now try to, this implies that x4 is fixed at 0. So, we can now show that every corner point is actually got by fixing these values at 0 and not at any other non-negative value. To put it differently, it makes sense only to fix these at 0 and not to fix these at any other value other than 0, any positive value other than 0, because by fixing them to any positive value other than 0, we end up evaluating a point which is inside the region. And we now know that any point inside the region is not important to us, because every point inside the region is going to be dominated by a corner point. And since we are going to look only at corner points, we do not have to fix it at any other value other than 0. So, in the algebraic method, when we fix some variables to a value and then solve for the remaining, we fix them only at 0. Now, these 6 solutions that are obtained by fixing them at 0 are called basic solutions. So, in the algebraic method, after we convert the inequalities to equations and when we solve for a certain number of variables by fixing the remaining ones at 0, we get basic solutions. So, in this example, there are 4C2 or 6 basic solutions. In general, after converting them into equations, if we have n variables and m, after converting, if we have n variables and m equations, then we have NCM basic solutions. So, in this example there are 4C2 6 basic solutions. Now, any other solution that is evaluated by fixing them to any value, any one of them to any value other than 0, any positive value other than 0 is called a non-basic solution, and we are not interested in non-basic solutions at all. Now, there are 6 basic solutions that we have looked at. Out of these 6, we realize that 4 of them are feasible and these 2 are infeasible. So, those feasible solutions, what is a feasible solution? Any solution that satisfies all the constraints including the non-negativity is a feasible solution. So, out of these 6 we find that we have 4 solutions that are feasible. So, those basic solutions that are feasible are called basic feasible solutions. For example, if we look at a point here, say 1 comma 1, it is a feasible solution, but it is a non basic feasible solution. We are interested only in basic feasible solutions. The remaining 2 which are not feasible because these values violate the non-negativity restriction. Now, these have to be called as basic infeasible solution. They are not usually called as basic infeasible, they are just called infeasible, because when a solution is infeasible, it does not matter whether it is basic infeasible or whether it is non-basic infeasible. I mean, typically you can show that some of these points are actually this point and this point, which are not of concern to us. It does not matter whether we are looking at this point or this point, there is no need to categorize them once again saying this is non-basic and infeasible, this is basic and infeasible and so on. So, if we are interested in basic feasible solutions, any basic solution which is not feasible straight away becomes infeasible. So, we have 6 basic solutions in this example, out of which 4 of them are feasible and 2 of them are infeasible. We can also show that all the basic feasible solutions correspond to the 4 corner points that we have. Now, these 4 basic solutions that are feasible are 1, 2, 4 and 6, and they are the 4 corner points 1, 2, 4 and 6.
What is the guarantee that fixing some variables will cause the other set of equations to be consistent or to have a unique solution?
Okay, right now we are explaining this assuming that there is a solution to the problem. Later we will look at situations where the linear programming problem may not have a solution at all. Now, those aspects will be taken up during that time. Right now it is under the assumption that a solution finally exists. For example, we are not getting into situations about the singularity of the matrix and so on. You can always go back and say that when I am solving, for example, when I am solving for this, it means I am solving for x1 plus x2 equal to 5, 3x1 plus 2x2 equal to 12. Now, the implicit assumption is the rank of this matrix is not 1, and I do have a solution with respect to this. So, that is an assumption here. So, right now when we illustrate the algebraic method through this example, we have taken a convenient example where we have a solution to the problem. Much later when we work out the simplex method, we will show you examples where the problem may not have a solution at all. We will do that subsequently. Right now we are only trying to bring the one-to-one relationship between the algebraic method and the graphical method, and that is the purpose of this discussion. Right. So, we have 6 basic variables or basic solutions, out of which 4 are basic feasible and 2 are infeasible. We need to introduce one more terminology. Now, in this example, of these 4 variables that we have fixed these 2 to 0 and we have solved for these. Those variables which we fix to 0 are called non-basic variables, and those we solve are called basic variables. So, every basic solution has a set of basic variables and a set of non-basic variables. If we have two equations, then we have two basic variables, the remaining become non-basic. So, in this case there are 4 variables, 2 equations, 2 basic variables, 2 non-basic variables. If we had 5 variables and 2 equations, then you will still have 2 basic variables, the remaining 3 will be non-basic and they will be fixed at 0. Now, the corner points are basic feasible solutions, and we have already seen through the graphical method that the corner point solutions are important, and we have now shown that every basic solution corresponds to the corner point. Now, in the graphical method we said, having identified the corner points, all we need to do is to evaluate the objective function at these corner points and find out that corner point which has the best value of the objective function. So, we do the same thing in the algebraic method also. Now, we have already evaluated the objective function values for these 4 corner points. Now, the objective function values are 0, 25, 24 and 27. We are interested in maximizing our objective function, therefore, we choose this solution as the best solution which has the maximum value of the objective function. In this example, it turns out to be x1 equal to 2, x2 equal to 3, z equal to 27, which is the same solution that we obtained using the graphical method. So, let us go back to this. Now, we now go back and see that the 4, let us look at these. First what we do in summary for the algebraic method is we add the slack variables. We now have 4 variables and 2 equations. With 2 equations we can solve only for 2 variables. So, we have to fix any 2 variables to some arbitrary value and solve for the remaining 2. The 2 variables that we fix can be chosen in 4 ways. In each of these 6 combinations we can actually fix them to any arbitrary, resulting in infinite number of solutions that we saw, but we are going to consider fixing this value only to 0, and then we are going to consider only 6 distinct possible solutions which we have listed here, which we are going to show to you later. Now, the variables that are fixed to 0 are called non-basic, as I had indicated here, and those variables that we solve are called basic in these 6, and those variables that we solve are called basic variables. Solutions obtained by fixing the non-basic variables to 0 are called basic solutions. We have defined the basic solutions here by saying that we fix the non-basic variables to 0. Now, these are the 6 solutions that we have seen, the same 6 that are shown here, and among these 6 we find 4 are feasible and they are called basic feasible. The other 2 are infeasible, they are called infeasible, they are not specifically called basic infeasible. We are interested only in the solutions that are the values of the objective functions are now shown here. Every non-basic corresponds to an interior point in the feasible region that we saw, and in the algebraic method it is enough only to evaluate the basic solutions, because all the basic solutions are corner point solutions and the best value is optimal. Next, in summary, in the algebraic method we convert the inequalities into equations by adding the slack variables, and then we evaluate all the basic solutions for all the combinations, and we verify the optimum solution as the one with the maximum or minimum value of the objective function. Now, we said the graphical method is very good when we solve for 2 variables. Now, we now realize the algebraic method can be used to solve for any number of variables and any number of constraints, provided we are able to solve the linear equations. Now, are there other distinct advantages or disadvantages of the algebraic method? There are some distinct disadvantages of the algebraic method. 1, now we end up evaluating some 4C2, or in general we end up evaluating NCM basic solutions if after writing the slack we have n variables and m equations. Now, this is done in NCM ways. Now, NCM is a large number. NCM can become exponential when n is large and m tends to n by 2. So, we do end up evaluating a very large number of solutions before we reach the optimum. That is the first disadvantage of the algebraic method. Second disadvantage, very distinct one, is this: we evaluated 6 solutions here and we found that out of these 6, 2 out of these 6 were really useless and unnecessary. We did not look at these 2 at all. The moment the solution becomes infeasible, it does not add any value to the solution. So, if the algebraic method is good enough to a priori eliminate the infeasible ones, it will be much better off than what it is in its present stage. So, we need to look at a method which does not evaluate infeasible solutions at all and has an internal mechanism not to evaluate any infeasible solution. And in the algebraic, only after finding out a solution we realize that it could be infeasible, and then we are not interested in this. The other thing that happens is this: now there are 4 solutions here. If we look at these 4 solutions in the same order that we have seen, we first evaluated this, and the moment we have a feasible solution we will evaluate the objective function value, because that is what we are interested in. We are interested in the basic feasible solution which has the best value, or in this case the largest value of the objective function. So, first feasible solution that we looked at is this with z equal to 0. The second one that we looked at or we obtained is this, which gives me z equal to 25. Now, this solution to me is much more valuable than this, because this has a higher value of the objective function. Now, when I come back to the fourth, I have already seen the third, I realize it does not add value. I come back to the fourth, now I have got a solution which is basic feasible, but with z equal to 24. Now, this also does not add any value to me, because I already have something that is better than this. So, among my basic feasible solutions, I would ideally like my solutions to become better and better as I evaluate. I would rather not like to evaluate a solution with a lesser value of the objective function than something that I know, whereas this is the most desirable one, because this has a value better than this 27, and we stop. So, what are the disadvantages? 1, it evaluates a large number of solutions. 2, out of these large number, some of them could be infeasible, so we do not want to evaluate the infeasible ones in the algebraic. Second, among the feasible solutions, there are 4 in this case, we would ideally want the solutions to become better and better as we move, because we spend a certain amount of effort in evaluating the solution and you realize it is basic feasible, but then when you come to this 24 you realize it is not that important, because I already have something with 25. So, ideally you would want a method which would progressively evaluate better and better solutions. The last one is this: in the algebraic method, in this example there are 4 solutions. It turned out in this case that the 6th one, the last one that we evaluated, was the best. Now, what we would want is, just in case this had become solution number 4, then which means the third basic feasible solution that we have evaluated, I have got this 27. Now, if this 27 is the best one that I can get, then I need a mechanism which can tell me right here that you have got your optimum, you do not have to look at the remaining 2. So, we would want the algebraic method to be smart enough to be able to identify the optimum as soon as the optimum is found, rather than make you work the rest of the things, complete the entire NCM, and then at the end of it all make a comparison and then say this solution is better. So, basically we want a method which is better than the algebraic method that is shown here, which is better on 3 counts. 1, it should not evaluate any infeasible solution. Number 2, it should be capable of giving us progressively better solutions. We do not want, for example, to evaluate this 24 after we evaluate this 25. Third, the moment it has found the optimum, it should be able to terminate. It should not put you in a situation where even you do not know that the optimum has been reached, you evaluate the rest of them, and end of it all you realize somewhere here I might have found out the optimum. So, if there is a method which can do all these, then that method would add more value to the algebraic method that we have seen. Obviously, that method might require some more computation or extra effort. So, now there is a trade off between getting these 3 advantages if we can, and then spending some more time and effort to do that. Now, if we can get a method which can give us all these 3 advantages that we seek from the algebraic method, and if we are guaranteed such an advantage, then we do not mind actually spending a little more time and effort towards that method. Now, the next thing that we are going to see is that method, and that method is called the simplex method. It is called the simplex method, which is essentially an extension of the algebraic method, but the simplex method exactly addresses the 3 concerns that we spoke about. The simplex method will not evaluate any infeasible solution. The simplex method will give progressively better and better solutions, and the simplex method has an inbuilt mechanism to show that you have reached the optimum. So, before you enumerate or evaluate all possibilities, simplex would tell you that the optimum is reached. So, a simplex method is the most important tool that has come about, and that we will see in the next lecture that we meet.